Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4. We are on chapter 15, the phosphorus cycle, and we are looking at anthropogenic and natural sources of phosphorus. In many cases, lakes receive drainage and thus phosphorus from upstream lakes. That is, they are not headwater lakes. The portion of phosphorus input to a lake that leaves via outflowing waters is largely dependent on the lake's hydrologic budget, particularly its flushing rate. This, in turn, determines how much of the input is lost to the lake sediments. Since all but those lakes with extremely fast flushing rates act as nutrients sinks, downstream lakes receives less phosphorus as a result. Some surface runoff receives very large quantities of phosphorus from domestic sewage. The importance of this source varies greatly with population size and the efficiency of the treatment of the sewage for nutrients removal. Improved treatment in the form of tertiary phosphorus removal has reversed eutrophication in a number of well-documented instances in North America. Average values for the contributions via domestic sewage are given in Table 15-8. Industrial inputs, especially those associated with food processing, can be exceedingly high. So before we go further, let's look at this table here. Table 15-6. Export of nitrogen and phosphorus from soil of natural and agricultural areas. So on the left, we have the drainage basin type. We have then total dissolved inorganic nitrogen losses in kilogram of nitrogen per kilometer squared per year, and then total phosphorus losses in kilograms of phosphorus per kilometer squared per year. So what jumps at us here? For example, high-intensity pastures have very high nitrogen inputs. And in terms of phosphorus, I don't think there's any data for it. Arable lands, such as lands that are used for cash crops, there as well we have total dissolved inorganic nitrogen losses 4,000 to 10,000 kilograms of nitrogen per kilometer square per year. On the other end of the spectrum, areas with low nitrogen losses would be undisturbed boreal forest and general soil productivity. So for soil that have low productivity, we don't have much losses of nitrogen, which makes sense. In terms of phosphorus, high values of phosphorus, we have arable lands in the UK, the US, and the Netherlands. And we have also cleared forest, volcanic watershed. And groundwater leachates have a fair amount of losses of phosphorus, as well as urban runoff. On the lower end of the spectrum, we have undisturbed temperate forest. And undisturbed boreal forest actually has higher loss than undisturbed temperate forest, which is somewhat inverse to what's going on with the nitrogen. We have higher values in the disturbed temperate forest than in the undisturbed boreal forest. Mixed upland has low value. And then we have pretty high ranges sometimes, like pasture, low intensity, and intensive arable land here. All right. Ironically, cleaning detergents have been major sources of phosphorus that contribute marked vascularization effects to many freshwaters. Where legally permitted, synthetic detergents include phosphate builders as a major constituents, mainly sodium pyrophosphate and polyphosphates, to complex and inactivate cations of water supplies and permit more effective cleaning action. Before detergent phosphorus content was regulated, 7 to 12% of the weight of detergents was phosphorus, which contributed greatly to the load to waste treatment plants. In the United States, Canada, and the European Union, phosphorus has been banned in laundry detergents in some jurisdictions as long ago as the 1970s. The situation with dishwater detergent is less uniform, with some jurisdictions allowing low level of phosphorus. Where phosphates are banned as a constituent of detergents, the phosphorus loading to treatment facilities and surface waters declined by 50% to 80% groundwater. The phosphorus content of groundwater is generally low. Concentrations are about 20 micrograms of phosphorus per liter, or less, even in areas where soils contain relatively large quantities of phosphorus. The low phosphorus content is a result of the relatively insoluble nature of phosphate-containing minerals and the scavenging of surface phosphate by biota and soil particles. Table 15-7, so this is phosphorus budget for deep Arctic Tundra Lake and Toolik Lake, Alaska. So on the left side we have the inputs and then the exports, and then we have then the fractional phosphorus, total phosphorus, and the percentage of total, and the unit is in millimoles per meter square per year. So dissolved phosphorus present the bulk of the inputs to that lake at 3.28 millimoles per meter square per year. And in terms of precipitation, like this is a stream inflow. In terms of precipitation, a very low phosphorus, higher for particulate phosphorus than it is for dissolved phosphorus. And so total inputs of dissolved phosphorus of 3.37 and particulate phosphorus of 1.27, representing about 4.64% of the total phosphorus. And in terms of percentage of total, so independent of the value per surface area, we have like pretty high value of dissolved phosphorus from streams and then very low from precipitation. And total inputs, dissolved phosphorus leads compared to particulate phosphorus. Export, so how does the phosphorus is leaving that lake? And is living in, so there is some fraction that is staying in the sedimentation from the water column. And in terms of leaving it from a hydrological perspective, the dissolved portion is living at a higher value than the particulate fraction for phosphorus, which mirrors the inflows. So we see also dissolved phosphorus leading in the inflows of streams, and it's leading in the export of streams. And then the total outputs, so particulate is leading over the dissolved fraction, which is opposite in the import table there. We have dissolved leading over particulate. Let's go look at this table 15-8 where we're here. Surface water loadings of nitrogen and phosphorus per unit area from human excrements and other sources based on an average of 12 grams of nitrogen per day per person and 2.25 grams of phosphorus per person per day. So here, population density on the left, persons per kilometer square, nitrogen, and then phosphorus, and the units are in gram per meter square per year. So as the population density increases, we can see that the nitrogen and phosphorus loading increases, which is very logical. So for example, for a population density of 50 kilometers per person per kilometer square, we only have 0.22 of nitrogen and then 0.04 gram per meter square per year for phosphorus. Where if the population density increases to a value of 5,000, then the loading increases to a value of 22 gram per meter square per year for nitrogen and 4.05 gram per meter per year for phosphorus. Phosphorus in wet atmospheric precipitation and dry particulate material fallout originate from fine particles of soils and rocks. from living and dead organisms as volatile compounds released from plants as well as from natural fires and the burning of fossil fuels in atmospheric deposition. Phosphorus in wet atmospheric precipitation and dry particulate material fallout originate from fine particles of soils and rocks, from living and dead organisms as volatile or compounds released from plants as well as from natural fires and the burning of fossil fuels. In inland regions, the major source of phosphorus in precipitation is dust generated over the land from soil erosion. Phosphorus in wet atmospheric precipitation and dry particulate material fallout originate from fine particles of soils and rocks, from living and dead organisms, as volatile compounds released from plants as well as from natural fires and the burning of fossil fuels. In inland regions, the major source of phosphorus in precipitation is dust generated over the land from soil erosion and from urban agricultural and industrial contamination of the atmosphere. In heavily fertilized agricultural regions, the phosphorus content of precipitation is much higher during the active growing season than in winter, even in mountainous regions. However, nutrients accumulate in snowpacks and on the ice during winter and can be released rapidly in large amounts during the spring thaw. Although the total phosphorus content of precipitation is generally low, about less than 30 micrograms of phosphorus per liter in unpopulated regions, it can increase to well over 100 micrograms of phosphorus per liter around urban, industrial, agricultural environments. Even the lower concentrations are often substantially greater than that of the lakes receiving the deposition. Thus, atmospheric deposition of phosphorus can be a significant contributor to the overall phosphorus budget of a lake. Atmospheric contribution of phosphorus in wet and dry deposition range from approximately 0.01 to 0.65 gram per meter square per year, with most values in the lower portion less than 0.2 of that range of 0.2. These inputs can represent highly significant loadings when compared, for example, with the 0.07 gram per meter square per year value that Volwider estimated as a general permissible phosphorus loading rate for lakes. In some cases, atmospheric loadings of phosphorus can constitute 40% or more of the annual loadings. The relative importance of atmospheric inputs of phosphorus to the total input to a lake will be strongly influenced by the ratio of the lake's catchment area to the lake surface area, with smaller drainage to lake area ratios typically resulting in the increased significance of the atmospheric inputs. Phosphorus and the sediments, internal loading. The exchange of phosphorus between sediments and the overlying water is a major component of the phosphorus cycle in natural waters. There is an apparent net movement of phosphorus into the sediment in most lakes. The effectiveness of the net phosphorus sinks to the sediments and the rapidity of processes generating the phosphorus back to the water depend upon an array of physical, chemical, and biological factors. The correlation between the amount of phosphorus in the sediment and the productivity of the overlying water is modest to weak, and the phosphorus content of the sediments can be several orders of magnitude greater than that of the water. The important factors are the ability of the sediment to retain phosphorus, 2, the conditions of the overlying water, and 3, the biota within the sediments that alter exchange equilibria and affect phosphorus transport back to the water. Exchanges across the sediment-water interface overview. The deposition of phosphorus into lake sediments occurs via 5 mechanisms. 1. Sedimentation of particulate phosphorus minerals imported from the drainage basin. Most of this material settles rapidly and is deposited largely in nearshore areas. 2. Adsorption or precipitation of dissolved phosphorus with inorganic compounds via 3 mechanisms: phosphorus coprecipitation with iron and manganese, adsorption to clays, amorphous oxyhydroxides and similar materials, and C. Phosphorus associated with carbonates. It is difficult to distinguish the direct adsorption of dissolved phosphorus of lake water onto particles in the sediments from diagenetic and transfer processes within surface sediments. 3. Sedimentation of phosphorus with allochthonous organic matter. 4. Sedimentation of phosphorus with autochthonous organic matter. And 5. Uptake of phosphorus from the water column by attached algal and other attached microbial communities, and to a lesser extent by submerged macrophytes, with eventual transport back to the sediment by translocation and deposition with detritus. Once the phosphorus is within the sediment in various forms, exchanges across the sediment-water interface are regulated by mechanisms associated with mineral-water equilibria, absorption processes, particularly ion exchange, oxygen and other electron acceptor-dependent redox interactions, and the physiological and behavioral activities of many biota associated with the sediments. The sediment-water interface separates into two distinct domains. In all but the upper few millimeters of sediment, exchange is controlled by motion on molecular scales with correspondingly low diffusion rates. In the water, exchange is regulated by much higher and more variable rates of turbulent diffusion. The exchange rates between various deposits of phosphorus and the interstitial water of the sediment depend on local adsorption and diffusion coefficients and their alteration by enzyme-mediated reactions of the microbiota. Numerous processes operate often simultaneously to mobilize phosphorus from particulate stores to dissolve interstitial phosphorus and then to transport that dissolved phosphorus across the sediment water interface into the overlying water. Orthophosphate is bound to particles by physical adsorption as well as chemical binding of different strengths. Physical and chemical mobilization include desorption, dissolution of phosphorus-containing compounds, particularly assisted by microbially mediated acidity and ligand exchange mechanism between phosphate and hydroxide ions or organic chelating agents. Microbial biochemical mobilization processes include mineralization by hydrolysis of phosphate ester bonds, release of phosphorus from living cells as a result of changing environmental conditions, particularly redox and autolysis of cells. The internal loading of phosphorus to a lake from the sediments depend on hydrodynamic and biotic mechanisms that transport dissolved phosphorus from the sediments to the lake water. Because of the steep concentration gradients of phosphorus between interstitial water and the overlying water, molecular diffusion is a primary transport into the overlying anaerobic water. Currents from wind-induced water turbulence can disrupt gradients and resuspend sediment particles. Disturbance of sediments by benthic invertebrates living on or in the sediments and by bottom-feeding fishes when occurring in large quantities can cause appreciable bioturbation of sediments. Microbial generation of gases, particularly carbon dioxide, methane, and nitrogen, can accumulate from bubbles and rise to the surface. Such ebullition can disrupt gradients near the sediment-water interface and may accelerate the diffusion of phosphorus upward. The metabolism and growth of aquatic macrophytes living on and within the sediments can both suppress and enhance the transport of phosphorus across the sediment-water interface. Because of the major importance of the movement of phosphorus from large accumulation in the sediment to the overlying water, each of these processes is discussed in greater detail in subsequent sections. So let's look at figure 15-3 here. Processes involved in the mobilization of phosphorus from particulate stores into dissolved states of interstitial water of sediments and transport across the sediment-water interface into the overlying water. So we have the sediment here, and then we have the water, and then we have, therefore, that interface between the sediment and the water. And then we have particulate phosphorus, and then we have dissolved interstitial phosphorus here. So two different types of phosphorus. Like, so one is phosphorus that is on particles and or as particulate itself, and then we have the fraction of phosphorus that is in dissolved form in the water within the interstitial space, within the pore space of the sediment. Then we have physical chemical mobilization. So we have desorption, dissolution, ligand exchange, enzymatic hydrolysis. And so this is microbial mobilization. So this is enzymatic hydrolysis and ligand exchange, while this is a more physical chemical mobilization between desorption, dissolution, and ligand, and potentially ligand exchange being part of that as well. And then the upper part here, where phosphorus is leaving the sediment into the water, we have this transport mechanism: diffusion, wind-induced water turbulence, bioturbation, gas ebullition. So gas ebullition is a gas that is bubbling up, like it's kind of bubbling through the sediment into the water. Attached algae, cyanobacteria, and then rooted aquatic plants. And so those are like, all of these are like all the transport mechanism of dissolved interstitial phosphorus from the sediment into the water phase. And I think we're going to be leaving it today at this subchapter, oxygen content of the microzone, in terms of the phosphorus cycle in the sediment. And I'll see you tomorrow, and we'll start right from there. Thank you, and have a good day. Bye.